Hi, welcome back to this course, Computational Thermodynamics and Kinetics of Materials. Let's continue with some more ideas on phase diagrams. Today we will see what are phase fraction plots. Once it is done, most of the things about the basic phase diagram, how to visualize that are over. Then we can think about how phase diagram does not address several aspects. For example, the mechanism of transformation, we will treat that with an example of eutectic solidification versus solid state diffusion. From the phase diagram perspective, they are going to look same, but they end up in different kind of microstructures. We will see about that. Then we will see how kinetics complements phase diagram. Once it is done, we will summarize the understanding in the form of thermodynamics and kinetics. So what are phase fraction plots? So in a phase diagram, we have temperature versus composition. In a phase fraction plot, we are going to have phase fraction against temperature. So temperature here is in x-axis. So what happens in this is phase fraction goes from 0 to 1. If a material has a single phase, that the phase fraction of that particular phase is 1. Okay, that's how this diagram is going to look. It's a pretty useful diagram for a higher order system. Let's consider at a really high temperature, somewhere like this, it's going to be completely liquid. So we are having in the microstructure completely liquid. Then it is represented in the phase fraction plot like this, meaning it is against phase fraction of 1, it's completely occupying the microstructure. So this is liquid. Once it reaches the liquidus point, its contents start to decrease. So the phase fraction of liquid decreases, and obviously this point is going to be the solidus point where liquid completely vanishes. How the microstructure will look? In the microstructure, the moment it touches or crosses this liquidus point, some solid will form. So you can see some solid appearing, and this is how the solid content is going to increase. Right at the liquidus point, its content starts to increase as the liquid starts to decrease, and as the liquid starts to decrease further and further, the solid starts to increase further and further. So then eventually the solid occupies the microstructure, and predominantly it is solid here, you can see just before the solidus point, and once it reaches the solidus point, it becomes completely solid. So it remains as solid throughout the lower temperature region. So if there is solid state transformation, you can imagine this alpha phase content may decrease and some other phase content may increase. So that's how the phase fraction plot is going to look. How is it different? If you want to figure out the phase fractions in a binary diagram, you have to draw a tie line and apply the lever rule and things like that. But here these things can appear directly. So that this is quite useful if the moment the composition is fixed. So you can see in the y-axis or x-axis there is no composition. So if the composition is fixed and you want to visualize with respect to temperature how your phases change, their fractions change, you can use this kind of diagram. Let's say you want to decide the temperature for heat treatment to achieve a particular amount of one phase. Then you can use this kind of diagram to determine at which temperature you get the phase fraction at this desired amount. Right? Test your understanding with this. Phase fraction plot for iron 50 mole % chromium is given here. These are the questions. Are there solid state transformations? Think about that. What are the phases present at 400 degrees Celsius? So 400 degrees Celsius is here. Think about that. Can we read the compositions of these phases from phase fraction plot? Think about that. What is the primary solidifying phase? Primary solidifying phase means which is the phase appears just after solidification. From the liquid, which phase appears? That's the meaning of primary solidifying phase. Then, if the sigma phase is detrimental and needs to be avoided, okay, exposure of material to which range of temperature is not to be done. Okay, so industrially a very relevant question. If you want to avoid certain phase, you should not expose the material to certain temperature ranges. Okay, in this case, you want to avoid sigma phase. What is the temperature range that should not be experienced by the material? Okay, because if the material is exposed to that temperature, the detrimental phase is going to form. So think about what is the temperature range where sigma phase appears, and that's the temperature range that one needs to avoid, right? So the answers are this. For the first question, are there solid state transformations? Yes, you can see that there is BCC here. Once the liquid transforms to solid, this is BCC is the solid occupying the entire composition, entire microstructure. Then there is a temperature at which it starts to decrease and this red color thing appears, which is sigma phase. Okay. So obviously there is a solid state transformation, and at lower temperature even sigma disappears, BCC1 and BCC2 appears. So definitely there are solid state transformations. What are the phases present at 400 degrees Celsius? You can see at 400 degrees Celsius, you can read here, this is phase fraction of BCC2, this is phase fraction of BCC1. But at least you can see at 400 degrees Celsius, these two phases are there. So you can read their fractions here. So that these are the phases BCC1 and BCC2. Okay. So you have to be careful. This is not a phase diagram. In phase diagram, every pixel means something. This is not a phase diagram. Okay. So here, this is like a graph. It tells you how the y-axis value changes with respect to x-axis value. Okay. How the volume fraction of phases change as a function of temperature. Right. Can we read the compositions of these phases? Okay. BCC1, BCC2 phases are there at 400. Can we know the composition of these phases from this diagram? The answer is no. We can't. Because this diagram carries only volume fraction of phases against temperature, and this can be drawn only for one overall composition. The individual phase compositions are not available in this diagram. Okay. This is the phase fraction plot, not the composition plot. One can draw even that using the CalFed softwares, but this particular diagram, the phase fraction plot, does not carry any information on composition of individual phases. Right. What is the primary solidifying phase? It's BCC. That's the one appears once the liquid starts to transform to solid. Right. If the sigma phase is detrimental and needs to be avoided, exposure of material to which temperature range is not to be done? This is the temperature range. The range over which the sigma appears, about 500 to 820 or so, 820, 830. That's the temperature range you should avoid. Okay. Let's say you are doing a heat treatment at a high temperature BCC and you are stabilizing or homogenizing a single BCC. Then you want to cool from that temperature to low temperature, then start using it. Okay. But how do you cool after the heat treatment? You can't simply cool in a furnace with the slow cooling. Let's say you keep the material inside the furnace and switch off the furnace so that it slowly cools. If that happens, the material will experience this temperature range at least for a small time. That may be enough for the sigma phase to nucleate and grow. Okay, sigma phase can start forming. That's a problem. If you want to avoid that, better you do a very rapid cooling from high temperature to low temperature so that you don't give any time for this sigma phase to form. Okay, we haven't seen about the kinetics in detail yet, but there is something called kinetics that you at least know by now. There is a rate at which sigma will form. But if you don't give any time for sigma formation, then it means you are suppressing the sigma phase formation, at least kinetically. Thermodynamics says that, or the phase diagram tells that, if you expose the material to this temperature range, sigma will form, but it doesn't tell you how fast sigma will form. Okay, so if sigma phase formation temperature range is avoided, let's say we cross this temperature fast, then we can avoid this sigma phase from appearing. So that's one way of looking at this diagram practically, right? Now this phase fraction plot is now compared with the phase diagram. I said this is iron chromium 50 mole %, which is this overall composition line. So this is our single composition for which we have drawn the phase fraction plot. But what happens in this binary diagram, you can see liquid is stable here, liquid is stable here. Then liquid to solid transformation happens. So this is where that liquid to solid transformation happens. The temperature, you can see the range of solidification here. Then there is a big temperature range over which single phase BCC is seen. So that's what is here. So this, for this big temperature range, single phase BCC is stable. Its phase fraction is 1. So that completely occupies the microstructure. Then there is a temperature range over which we see sigma phase appears. So there is this, say, BCC plus sigma for a small region, and then complete sigma for a big region. So this is the temperature range over which it is completely sigma. Then it enters into a two-phase region, BCC1 and BCC2, which can also be seen here, BCC1 and BCC2. Okay. So one to one, you can see how this phase fraction plot relates to the phase diagram. But in this, it is straightforward because the binary phase diagram is available. Where these sort of phase fraction plots are really useful is in the multi-component domain, where you can't even have, or you can't even visualize a binary, you can't even visualize a phase diagram. Let's say if it is a 13 element phase diagram, something like a nickel based superalloy, even 15, 18 elements. How do you visualize the phase diagram? But if the composition is fixed, you can at least see what phases are stable at what temperature ranges. So that's the kind of use for this phase fraction plot. Phase fraction plots, they are representing phase fraction against temperature. The fraction of phases can be seen directly, that is the advantage. This is useful for practical multi-component alloys. So now that we have covered many of the fundamental things about phase diagrams, we'll see about things that are not that easily available in phase diagrams. Okay. So one such thing is mechanism of phase transformation. Let's consider this kind of diagram, a simple eutectic system. Here, the initial state or the overall composition is 50% of A and 50% of B, and temperature is below the eutectic temperature. Okay, somewhere here. Okay, this is the temperature. This is going to be the material now. So in this, if you want to reach that final state, we are going to reach it through two different routes. The first one is through eutectic reaction. So we are going to do the solidification through eutectic reaction. So how do we see this? Again, take the 50% A, 50% B material. This is our initial material. So this is some amount of A, some amount of B. They are equal in amount, A and B. So take them. It's initially the mechanical mixture. That's the initial state, meaning they have not reacted or dissolved into each other. So this is our overall composition now. So this is like the average of these two, right? Then we take that pure elements A and B to really high temperature. Take pure A, take it to this really high temperature, it's going to become liquid, and B also, the pure element B also is going to become liquid, right? If they are allowed to react at that temperature, dissolve at that temperature, they are going to form a single liquid, right? And this single liquid is there above the eutectic temperature. And then if we bring it below this temperature, reduce the temperature and cross the eutectic line and go reach this temperature, what happens? So we are allowing the eutectic reaction to happen. So it's going to look like this. Below the eutectic temperature, it's going to undergo the eutectic transformation. It will form alpha plus beta eutectic product. Often it has this kind of a morphology, alpha beta. The yellow and purple phases are represented here as alpha and beta. Okay, so this is how a eutectic reaction product will be. So this is the final state now. In the phase diagram, we don't see this morphology. What we see is this point, and in this point, what we can conclude from phase diagram, we are going to only say this point will have two phases. One will be alpha, one will be beta. The liquid, the composition, overall composition of liquid is going to separate into two phases. One phase will have this composition, the other phase will have this composition. If we want to apply the lever rule here and calculate the phase fraction of alpha and beta, we can do that. We will evaluate some amount of alpha and beta. Right. So this diagram gives only this kind of information. It doesn't talk anything about the morphology. Remember that. Although we say eutectic reaction is going to happen from the phase diagram, we are not very sure about this microstructural morphology and all, because we said often it comes in this eutectic product, this lamellar kind of structure, but it need not be. Eutectic product need not be lamellar every time. So what we have seen is about TE, through the eutectic reaction or solidification, pure metals melt and dissolve to form a single phase liquid at high temperature, and during cooling below the eutectic temperature, eutectic reaction occurs, liquid transforms to alpha and beta. Alpha plus beta appears with the phase fractions and compositions as shown in phase diagram, right? So this last sentence you can focus. This is just the information from the phase diagram. Okay, we are going to repeat that after the next example as well. So this is the next one, where the same final state will be achieved by solid state diffusion. Okay, we are going to take 50A 50B again, like this, 50A 50B. Then what we are going to do is, we are going to join them like this. So these two are joined and they are kept at temperature below eutectic temperature, meaning at this temperature they are going to be kept. So pure B piece and pure A piece will be taken, they will be attached like this, and since this temperature is significantly high, the diffusion will happen in the solid state between them. So we will see about diffusion in detail in future. So that's called interdiffusion of elements into each other. This will happen in the solid state. So atoms jump and move from one solid to the other. So that happens at this temperature, and alpha and beta phases will eventually appear, but they are not through the eutectic reaction. Okay, you see the purple phase and yellow phase, they will form because some B dissolves into A and some A dissolves into B, so that we can say that this is alpha phase and beta phase. You can see the alpha phase and beta phase appears. So alpha plus beta is not eutectic product now. It has not formed through crossing this horizontal line from liquid state. It directly formed here at this temperature from solids in solid state. So there is no point of crossing this line here. Okay. So in that way, this alpha composition moves here, and the beta's composition is going to be here. So the B piece is going to accept this much amount of A, and the A piece is going to accept this much amount of B. That's how the alpha and beta appears. So it is not through eutectic reaction. So in this case, what happened? Pure metals interdiffuse to form alpha plus beta. And eventually the final sentence is same between previous case and this case. Alpha plus beta appears with the phase fractions and compositions as shown in the phase diagram. Even at this temperature, you can apply the lever rule, you can apply the tie line, figure out the composition and phase fractions, they are going to be same. So what is the difference then? Phase diagrams only give the name and number of phases, their fractions, compositions, nothing more. Phase diagrams do not give information on the morphology of phases. You see, this morphology aspect does not come from the phase diagram. Okay? You can see in the previous case, it was not having the lamellar structure at all. If you see the interdiffusion case, it does not have the lamellar structure at all. Right? So the morphology aspect doesn't come from the phase diagram. So it is more to do with the mechanism of phase transformation rather than the information from phase diagram. Right, that's about the mechanism. And a very related idea is kinetics. Kinetics is to do with the rate of transformations. So if you see in both of solidification and solid state diffusion, the final state is the same. In phase diagram, which of the two is faster transformation path? That's an interesting question to ask. In general, solidification is faster compared to diffusion in solid state. So is this rate or time aspect? So we are talking about which is faster. Okay, the rate or time aspect is there in this question. Is that aspect available in phase diagram? The answer is no. Such answers are given by kinetics of transformations. So kinetics provides the answers on the rate of transformations, right? So this is how kinetics will complement the phase diagram. To summarize our understanding over the last few classes, phase diagrams indicate a map of conditions and corresponding stable phases. Conditions in the sense state variables and corresponding stable phases. So this is called as phase stability or equilibrium diagrams, and it's the subject matter of thermodynamics. Okay, we will see in the upcoming week fully focusing on thermodynamics, and then how it is related to phase diagrams. The subject matter of kinetics is the rate of transformations, right? So both these things are important. So this thermodynamics and kinetics is very important for us to proceed further. So in the next week we will spend time on thermodynamics, and then will go to kinetics. Thank you. I hope the lecture is useful. See you in the next class.